Good morning. I hope you all are doing well. Happy Wednesday. What we're going to do today is start the beginning of 3 days of kind of an overview of this section for Midterm Exam 1, which will be next week. So yesterday, if you had lab with me, we talked briefly about this, and today, if you have lab with me, we'll talk more about it. But what we're going to do is start getting ready. We'll go over some review questions, stuff like that, and see what's happening. And some of you have had midterms from me before, and some of this will be really boring, but not everybody has. So I want to make sure that everybody's up to speed. In this exam, the most important thing is that there will be some parts to bring that are not necessarily things that you usually bring. So definitely bring a calculator along with you. A pencil will be definitely helpful. A Scantron is needed next week. And in the bookstore, if you go there, there's a whole bunch of different types of Scantrons. As long as you buy a Scantron from the bookstore with 100 questions total, you're going to be fine. So that would be 50 questions on the front and 50 questions on the back. And there's a red version and a green version and an essay one and stuff. But as long, again, as you buy one from our bookstore with 100 questions total, you're good to go. And while you're there, get a couple of them, all right? We'll need a couple throughout the term, so it'll keep you from going back in, getting them. If your class is Tuesday morning, all right, I highly recommend that you get it before Tuesday. So get it Monday or today or something like that. The exam starts at 8 o'clock for you, and of course, that'll be part of your exam time, and the bookstore opens at 8, so there'll be a delay if you buy it Tuesday morning. So make sure you get it ahead of time. That would be my one recommendation. And then the lab we're doing this week, the acids and bases titrations or intro to acids and bases, that lab will be due next week when you take your midterm. Now, if you had lab with me yesterday, you've already done it, but if those of you on Wednesday, we'll do it today. And then exam prep 1 is another thing that'll be due for you next week at the time of your midterm. And again, some of you have seen these from me before, but if you haven't, right after problem set 3 in your companion or online, you can download this handout. It's basically a double-sided single-page handout. And what most of that's about is there's a question, and it shows you the answer. And your goal is just to show how you go from the question to the answer. So show your work, all right? And I don't mind answering questions on exam preps whatsoever, and some of you have already done that, which is cool. I'm hoping when you see the exam prep that most of it will be pretty basic, but if it isn't, that's when you definitely ask other people and stuff to see what's happening. Now, the exam format will have 20 multiple choice questions, and there's 5 short answer questions. So it's a combination of multiple choice where you'll pick the best answer of amongst the 5. And there's also a part where you'll show your work, and partial credit will be a big time there. So make sure that you show me how you set it up, show me the steps you're doing, stuff like that. It'll be just under 2 hours in length, so we'll do that. And then you'll take your exam next week, either Tuesday or Wednesday, whenever your lab section is. And I should be able to return it to you the following Friday, a week from this Friday, in lecture. And the end of it, there'll be a summary sheet. And the summary sheet just says how you're doing in the class as of this time. And please check that out, all right? Make sure that the scores that are entered are the scores you actually got, in case I made a mistake. Also, if you're missing a lab, stuff like that, it'll post it there. And make sure you turn your labs in, even if they're late, to get lab completion and stuff like that. There will be a brief lab afterwards. It's very similar to the lab we're doing this week. So for those of you that had lab yesterday, you have all the skills now. It should make next week's lab really chill. On the other hand, for those of you with lab today, you don't know what I'm talking about. We'll go through how it works. It's pretty mellow. Next week's lab is just a worksheet lab. There's nothing to type up. This lab will be something to type up. Any questions on this kind of stuff? Cool. In addition to what we're doing right now, all right, in the companion, there is a sample midterm exam. It was from an exam I gave a few years ago. I think the sample midterm exam has 25 multiple choice questions, while yours will have just 20, all right? But with that exception, it should give you a good sense as to what the midterm will be like. And for that sample midterm, the answers are provided. So what I would do is literally like print off the exam and just go through it, all right, and see how you do. Check your answers and stuff to see. And it's a good study thing to make sure that the concepts are good, and it also will hopefully help you to see the areas where you're stronger and weaker. There's another midterm exam under quizzes and exams. It's kind of a cheesy one, but it's another way to study and stuff too. So lots of ways to get help and assistance. Any questions on any of that? Cool. So without further ado, let's get into the review. And again, how this will work is I'll put up a question, I'll wait a certain amount of time, I'll allow you to actually work on it, and I encourage you to work on it. If you have your iClicker, you can participate by selecting what you think is the right answer, but even if you don't, it's no big deal. Just on paper and stuff, make your best guess what it is. We'll talk about what the actual answer is. And again, I don't care if you get it wrong or right or anything like that. This is all about making sure that what you have is solid and stuff and good. Okay, so here's an example of a type of problem and stuff that you could see on the midterm. We have 0.010 moles of dinitrogen tetroxide. It's in a 2-liter flask at a certain temperature, and after reaching the equilibrium, the N2O4 has that value. So see if you can figure out what K sub C will be for this reaction. And it will be one of those 5 answers up there. So see if you can figure out what it is. After a little bit, we'll talk about how to solve it and stuff. So. Passing back papers for section 1. I forgot to return them yesterday in lab, so don't get any papers, it doesn't even know. Very cool. On a reaction like this, the ice table helps out a lot, all right? Because you're looking for the equilibrium concentrations, the E of the ice table. And these numbers will go into the equilibrium expression, products over reactants, squaring the NO2 because of the stoichiometry of 2, only put gases and aqueous things in here, no liquids and solids. And one little hint that I wanted to give you is that in an ice table, make sure you use moles per liter. So you'll use 0.010 moles divided by 2 liters, and that number is the actual initial concentration of N2O4, so 0.0050. And in a problem like this, you don't start with any NO2, all right? It would explicitly state you're gonna have the NO2. And then you can see here how N2O4 at equilibrium has this value, 0.0038, all right? And from here, then, we kind of have to think a little bit about what's going on. And it comes down to stoichiometry. And if stoichiometry isn't a term you use at your dinner table, which I understand, stoichiometry means like 1 N2O4 reacts to make 2 NO2s. It's the ratio of the coefficients, or the moles. And why that's helpful here is that for every X N2O4s that are used up, you're going to create 2x of NO2s. The change line is based on the stoichiometry, those numbers. And there's like an invisible 1 in front of N2O4 and a 2 in front of NO2. And that's saying that 1 N2O4 is used up for every 2 NO2s that are formed. So instead of 1 and 2, you can use x, all right? So for every x N2O4s that are used up, you're going to create 2x NO2s. So to get this number down here, which is what we need to place in there, we already have this number, all right? We just need that NO2. We need to figure out what x is. And you can probably see that this minus x equals this number, all right? So if you take this minus this, it will allow you to solve for the value of x. And then whatever that x is, 2 times that number, excuse me, is going to go right there. So when I did this and stuff, here's my little cheesy ice table. All right, N2O4, again, moles per liter, 0.0050. When you solve for x, it's like 0.0050 minus 0.0038, which is 0.0012. So x here is 0.0012. And again, what that means is that 0.0012 moles of N2O4 were reacted per liter. And in the process, twice that number, or 0.0012 times 2, 0.0024 moles per liter of NO2 were created. That's just actual numbers for that 1 to 2 ratio. So this number is 0.0024. And then if you take 0.0024 and square it, and you divide by 0.0038, it should be good to go, 1.5 times 10 to the minus 3. Is this reaction a product-favored reaction or a reactant-favored reaction? Reactant, that's right. When K, the value is less than 1, it means reactant favored. So that means in this case, you would have more N2O4 than you'd have NO2. If K was larger than 1, you would have a product-favored reaction. Does it make any sense to have a negative K? No. Remember, the K is literally products over reactants, all right? Some kind of chemicals, some kind of moles, some kind of mass. And you can't have negative mass in chemistry, so your K values will never be negative numbers, all right? They could be greater than 1, they could be less than 1, but they won't be negative and stuff, so. Any questions on that? There's lots of things, of course, you can do with equilibrium constants and equilibrium constant expressions. This is kind of a cool example where you're taking 2 different kinds of equilibrium expressions. And the first is nickel 2 carbonate, and it's breaking down to nickel 2 plus and carbonate. And here's the K value for that one. And you're combining it with a second reaction, which is essentially a Ka for hydrogen carbonate. But anyway, hydrogen carbonate reacts with water. It makes carbonate and hydronium. And you can use these two K values here to find the K for a third reaction, which doesn't look a lot like either one of them. And in this one, we're trying to see what the K is to dissolve nickel carbonate. So nickel carbonate is kind of basic. We're essentially adding acid to make all of this stuff right here. See if you can figure out which one of these equilibrium expressions best reflects this reaction. And what you're going to want to do is combine these two Ks to give you this reaction, and then manipulate the actual K values to find what the number will be. This kind of problem is kind of like what we did back in Chem 221 with Hess's law. And some of you may not have taken Chem 221 for a while, but in Hess's law, we combine different reactions together to give the delta H of an overall reaction. And that's kind of what we're doing right here. When you're doing these kind of problems, keep your eyes on the prize. And what I mean by that is that you want to take the first two reactions and make it look like this thing right here. And to keep your eyes on the prize, all right, I try to find things that are similar in both reactions. So for example, in the first one, nickel carbonate, nickel 2 carbonate, is only a reactant, and we want it as a reactant in the desired reaction, all right? Also, if you look at this one, the nickel 2 plus as a product, we want nickel 2 plus as a product here as well. So even though carbonate doesn't show up, and that can be a little weird, I think we're gonna leave that reaction just as it is. Because if I was to flip it or multiply it by a coefficient or something, I would change what I'm looking for down here, and that would be probably pretty weird. But the second reaction, when you look at it, we see some things that are similar, but they're kind of awkward. And what I mean by that is hydrogen carbonate is present in the reaction, but unlike hydrogen carbonate being a reactant, which is how it's written, hydrogen carbonate is a product. And if you look at this long enough, you'll also see that hydronium, which is a product right here, is a reactant in the desired reaction. So I won't be able to just use this reaction as is, all right? I kind of want to flip the reaction. I want to turn reactants to products and products to reactants. So if you see this kind of thing where things are flipped around, then what I do is I just rewrite it, and I'll write products as reactants and vice versa. So carbonate and H3O plus make hydrogen carbonate and water. And I'm going to just erase this reaction because I don't want to get myself confused with how this works out. And if you do this now, all right, you can now see how, hydronium is now truly a product, and hydrogen carbonate is now truly a product as well. And actually, here's water as well. Woohoo! Bonus point. Now, carbonate, you can see in the new reaction, is a reactant, but I had carbonate up here as a product. So when you add this together, it's like having X on both sides, and you can subtract X. So carbonate cancels out in the overall reaction. And so by reversing that reaction, I then have nickel 2 carbonate plus hydronium, making nickel 2 plus hydrogen carbonate plus water. So we need to flip that second equation to make this work. This is the K value for the second one, and this is the K value for the first one. 6.6 times 10 to the minus 9 is good as is. I haven't done anything to that equation. So down here, I'm going to use that number as is. I didn't use anything to that reaction. But what do you do to the K value if you reverse the reaction? Flip it. 1 over inverse, I heard back there. Yeah. This one right here is going to be 1 over 4.8 times 10 to the minus 11th. And when you add equations like this, you multiply the k's together. So 6.6 times 10 to the minus 9, I'm going to multiply by 1 over 4.8 times 10 to the minus 11th, or 6.6 10 to the minus 9 divided by 4.8 10 to the minus 11th. And when you do that, I had the answer of 140, all right? So you can see down here, here's the regular K, and here's the 1 over the second K in order to find out what it is. This is cool. Nickel carbonate. Carbonates, like lots of things, are bases, all right? And they react pretty readily with water, so we would think that this might be a product favored K and stuff, so. Any questions on how this works? As a chemist, this can be kind of cool because it allows you to find an equilibrium constant, which might be difficult and stuff, and you can just manipulate known values of things around. So. this problem is a pretty tough problem. So I want to talk about how you would approach it, and I'm going to give you some time to work on it. But I'm also going to let you know that to really do this right, it can be tricky. However, as an aside, there's a quick and dirty that makes this one easy. So what I'm going to do is we're going to talk about how you would do it, and I'll give you some time to work on it. See if you can figure out the quick and dirty. And if you can't, then don't worry, sit back, relax, and enjoy it. Here we have a reaction, 2 reactants and 1 product, and an equilibrium constant. And we initially have all 3 chemical species present. So it has reactant and product. Those are the initial concentrations, and what you want to do on this problem is find the equilibrium concentrations of all 3. Now, what you need to do on this problem, conceptually here, is you first need to figure out if the reactants are going to move towards the products, or if the products are going to move towards the reactants. And that's a Q versus K calculation. So the first thing you should do here is go Q, products divided by reactants, and compare that to the K value which is given. If Q is less than K, then that means reactants will move towards products. And in the ICE table, the H2 and the I2 will have like minus X, and the H2 would have a plus X. But it could be that Q is greater than K, and that means your products are going to decompose and make more reactants. So see if you can do this. This is kind of a tricky one, but I want to show you how this all works, and these are the kind of things you can do with equilibrium. So I'll shut up and let you work. I want to start talking about this problem and why it's a little weird compared to some of the stuff we've seen before. So in a problem like this, if you set up an ICE table, which is definitely part of this problem, you'll have initial concentrations of H2, I2, and HI. Now, most of the problems we've seen, we had like maybe 2 of the 3 or only one thing, and then it's pretty easy to figure out what's happening because at equilibrium, you have to have non-zero amounts of everything, all right? You have to have non-zero amounts of products and reactants. So when you start to write out the ICE table, you have these concentrations. The question is, do you have negative x, positive 2x, which means that the reactants will go down and the products will increase, and that's very common. But you could also have positive x, and negative 2x, which means that at these conditions you have a lot more HI than you have reactants, and the products will shift to the reactants. So it's unclear what your values of C should be, like which ones will be positive and which ones will be negative. Now one side will be like negative and positive or negative and positive, but we don't know like which one it is. And this is one place where Q really helps out because you can use these values, figure out a Q, so this squared divided by H2 and I2, that's what the Q value is, and we'll compare it to the 54.3 number. Once we have that, then we can figure out what the X values are going to be, which ones are negative, which ones are positive, and we can go through and solve for what the equilibrium concentrations are going to be. So the punchline is that the answer is D. Woohoo! But let's talk about now how you could get to this answer D. And the first part, like I said, is you've got to use Q, all right? Because you don't know if products are going to go towards reactants or reactants are going to go to products. If you have all 3 present, then this is something that's kind of common. So I put in the values for HI and I squared it, divided by H2 and I2, and it came out to be 69.7. And 69.7 is larger than K, 54.3. So what that tells you, if Q is larger than K, then the products will start shifting towards the reactants. Like you have too much product at this equilibrium value relative to the reactants. And what that means then is now I can assign the X values because products are going to break down and more reactants are going to form. So the only way to tell where the negatives are on the left and the positives are on the right, or in our case vice versa, is through this Q versus K. And if Q in this case is larger than K, less products, more reactants, the reaction shifting to the left, stuff like that. Questions? All right, once you have this, then the rest of it is just a normal, quote-unquote, equilibrium thing. You can set up the equilibrium. Notice here how here's positive x and minus 2x. So here are the equilibrium values. And then just like we've seen before, this is just how to set up the equilibrium constant. Products at equilibrium divided by reactants equals 54.3. This is a quadratic formula, so you can put it in your calculator to get the solve, or if you have the quadratic function, you can solve for it. You get 2 values of x. One of them is positive, one of them is negative. Negatives don't fly in this section, so just ignore that one. Your x is this number. So then you can go back up here and add this amount to the 0.00623 to get this number. You'll subtract 2x from the HI to get that value, and you're good to go. Now, this is weird, but I want to share with you a really cool hint that sometimes will work with these. If you take these 3 numbers and plug them back into the equilibrium expression for K, so products squared divided by reactants, you're going to find that K comes out to be 54.3. And in that initial set of combinations of H2, I2, and HI, you can actually pump all those different numbers in there and see which one comes out to 54.3. So let's go back to this. Oops, hold on, I got to think too fast there. In this problem, if you're looking at this and you're like, blah, 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 blah. All right, and I understand completely because it is spring term and it's nice outside. But anyway, one thing that will sometimes help is if you go straight to the answers. This is the joy of the multiple choice question. Don't throw tomatoes at me. You can literally put the hi squared divided by h2 and I2 and look for a k which is close to 54.3. And if you do that, d comes out to be 54.3. So that's a super kind of funky, under the fence, kind of quick and dirty way to do it, but it is obviously a lot easier than going through the official way, which again is to find q, you set up the i's table, solve for the quadratic, but you can at the very least like check your answers. If you've done it right, it should be 54.3. I put this up here because a lot of you are interested in biology, and a lot of times in the wild, all right, there'll be a combination of chemicals already present, and through intentional or unintentional means, something will be added, and it's nice to know if the reaction will shift towards reactants, or like it did in this case, or towards products, which is also common. So, any questions on that? So let's change gears a little bit. This is an example of how Le Chatelier's principle is something we'll talk about quite a bit. And we've got this reaction right here. It has a delta H value, and there's also a K sub C. And we're going to take the temperature, and we're going to cool it down. We're going to decrease the temperature. What do you think is going to happen to K? Do you think it'll go up, it'll go down, or will it stay the same? If delta H has a negative number, does that mean it's endo or exothermic? Ooh, we're hearing a lot of different answers. Good. This is why we review. All right. I want to make sure that everybody's up to speed. I appreciate everybody that participates. So delta H is enthalpy. All right. And as heat is released, all right, that really isn't appropriate, but let's do it anyway. If heat is released, it's like trying to get rid of it. Negative delta H means exothermic. Heat is released. That's why I was giving you the throw up sign. I'm not really, saying, well, maybe I am. Anyway, I'm on medication. Prop that back on. So in this case then, if you see delta H is negative, exothermic, all right, heat is given off as a type of a piece here. So you can literally write in an exothermic reaction where delta H is negative, you can literally write heat as a product, all right? Because exothermic means it generates heat, all right? It's being given off. So in this reaction, we're cooling the reaction down, all right? And that's kind of like taking heat away from the reaction. And if you take the heat away from an exothermic reaction, you're taking something away from the product side. And like we've seen, when you take away something, the reaction shifts to the side that you're taking it away from. So in this case, the reactants will be shifting to the products. You'll end up with more products and less reactants. And more products means that K is going to get bigger, all right? K is products over reactants. Your products will get larger, your reactants will get smaller. That's what that means. So this is cool. This is a good discussion. Negative delta H, exothermic, heat is a product. Positive delta H means endothermic, heat would be a reactant. And the conditions would be quite different if the reaction was endo versus exo. If it was endothermic and you took heat away, you make more reactants, your K would decrease. Okay. Any questions on that? Sweet. Here's an example of a type of problem from the acid-base section. You're adding 0.535 grams of sodium hydroxide to 100 milliliters of water. What's going to be the hydronium concentration? Now again, it's not hydroxide concentration, but hydronium. See if you can figure out what that's going to be. Okay, I'm running out of time, so we'll have to start with this question on Friday. The answer here comes out to be B. A is the concentration of hydroxide, but not hydronium. So Kw equals hydroxide times hydronium. We will talk more about this on Friday. Sorry, I started here kind of late. We'll do this more on Friday. Have a good day. I'll see you soon.